Welcome back to CS 520. In this session I'm going to talk about implementing the maTe virtual machine. And again, this is going to build on the last two videos, and I'm going to steal one of the slides, in fact, just to remind you of the big context here. Alright, here's the big picture that we're talking about implementing this virtual machine, and it consists of a bunch of components. We've already talked about the initialization of the VM, reading the class file, and implementing a set of functions to provide access to the information in the class file. And what this video is going to do is fill in the rest of the picture. There's an execute engine that executes instructions that sits atop of these three components: the class file access functions, a set of functions to manipulate the heap, which is the location where we store objects that the program is creating and manipulating. There's a garbage collector associated with the heap, but we're not going to talk about that in this lecture. There's a separate lecture on garbage collection. And then there's a component that represents frames, which is blocks of data that are concern actively running methods. And finally, at the very bottom, there is native code that provides implementation of the four built-in classes that maTe provides. So that's the big picture. Again, we're going to try to talk about the heap, the frame, and actually implementing instructions. So let's jump right into it. The heap is the first thing. And the heap is just the name that we give where objects are actually stored. And since maTe is a pure object-oriented language, everything is in the heap then. There's no primitive types that are in the virtual machine anywhere else. Everything is an object, everything therefore is in the heap. And the key issue that we have to tackle is what's going to be the layout of the object in memory. And the design here is that each object will have a two-word header. The first word is the address of the class descriptor. So every object is of some class type. Okay? So we actually, in an object-oriented language, we actually record that type information at runtime as part of the object itself. So we always know at runtime what the type of an object is. Okay, and what is this? This address of the class descriptor is how we talk about classes. And if you go back to the class file, you'll remember that the class table contained the addresses of the class descriptors for particular classes. And the class descriptor, of course, has all the detailed information about the class, including the number of fields, the number of methods, and the address of the code for those methods. All right, that's sort of standard object-oriented implementation detail, that every object is going to have a class in it. What's non-standard here in this machine is because it's a pure OO language, we have to have native classes, these built-in classes I sometimes refer to as native classes, and we're going to need some help to implement those. And so that second word here in every object is a word dedicated to implementing a native object. So for instance, for an integer object, that second word will actually contain the value of the integer. Okay. Just a fine point here is that that word is used if it's an integer object or if it's any class derived from integer object. Okay. Because anything derived from integer object is an integer and has an integer value, and in all those cases the integer value will be in this second word. Okay. Collectively, I'll often refer to these two words as the header. After the header then is fields. If the class has fields, they will be stored in following words. Okay. Now it turns out that the native classes, for instance, have no fields. So in fact, the memory footprint of an integer object will just be, it will just be two words. Right, the class descriptor, address, and the second word, which in the case of an integer object contains the integer value. But if there are user-defined fields, then they will be following here. Okay. So again, I want to hammer away at that point, right? You know, what we're really doing here, the subtitle for this lecture should be, you know, revealing the magic of object-oriented programming, right? By implementing this maTe virtual machine, you're going to come out of this with a much better understanding of how Java and other object-oriented languages work. And it's the key thing here is what I just said a moment ago, is that we have runtime type information. Every object has its class encoded as part of the object, so we know what class it is. This is maintained at runtime. So in the terminology of 520, that means the interpretation of the bits in the object is added as a tag to the object. You know, in C, I'm often talking about, well, change the interpretation for this memory location by using a cast, which is a compile time construct, right? We ask the compiler to generate different kind of code to manipulate the object, but we have to do that in advance. In all languages, we can use the interpretation that's recorded with the object, and this makes it a little bit more dynamic, actually. So in particular, allows the same code to have different behavior based upon this tag. This is the magic behind virtual method calls. Let's take a moment to just talk about that. If we look at some maTe code, this is sort of the prototypical object-oriented programming example. Right, I can have an abstract class called animal, and I can have an abstract method called noise. Now, maTe doesn't actually have any abstract classes, so this is sort of simulated here. Right, and I could derive things from animal, and I can override the noise method. So pigs oink, dogs woof. Okay. And then what happens is in my program, then I can declare a variable of type animal. I can then, under two circumstances, in this case I'm just reading it a value from the input in order to distinguish two cases. So based upon the input value, which is the in operator gives me in maTe, if that in value equals 42, then I'm going to create a pig object and place its reference in X, which is of type animal. Otherwise, if it's not the value 42 that was input, then I'm going to create a dog object and put its reference in X. Now, this assignment is legal because animal is a superclass of both pig and dog, so it can receive a reference at either of those types. Okay. And then down below here, after the conditional, I can say out x.noise, and this is where the runtime type information is used. At runtime now, the virtual machine that's executing this can look at the runtime type, a type attached to the object referenced by X, and call the right method that will either oink or woof, depending upon what actually happened at runtime. Right? I couldn't do this at compile time, right? I couldn't pick the right one because it's dependent upon input data that I'm only going to know at runtime. Okay, so how does this magic work? That's the question. Well, it works through the magic of the class information that's available at runtime and the method tables that are embedded inside the class table. So I've just taken some of the assembly language. Remember, you can generate this assembly language yourself by taking a maTe source program. So if you're on Agate, you can run cs520/bin maTe compiler on animals.m for the maTe source program, and I can capture the output in animals.s for assembly language, and then I can look at this file. And this is an extract. This is not the whole file. I just grabbed the class table information about the 3 user-defined classes, and then I grabbed the code from the main block code section. Okay. Let me just finish the story though. Remember, you can then run the maTe. I forgot a slash here. You can run the maTe assembler to assemble the assembly language into a class file. So I can run, this is my handwriting, of course, is terrible. That's MAS, MAS. So I run the maTe assembler, I redirect animals.s and redirect the output to animals.class. Now I have a class file that can be loaded into your virtual machine. But anyways, looking at the class file through the lens of the assembly language, because it's in human readable form, I can see what the compiler is up to that makes this all work. First of all, the three classes inherit. If we look at their class descriptors, we'll see their superclass object for animal, and then pig is superclass as animal, and dog superclass as animal. The number of fields is 0 in all these cases. The number of methods is 4 in all these cases. And the first three methods in each class are inherited from object. We see that by those munged names, actually. And what the compiler does to make this work, virtual methods to work, is it puts the noise method in the same location in the table. It's always the fourth entry in this table for both pig and dog. Okay, but when you look internally, you'll see that for pig, it's obviously the pig version of the noise method, and for dog, it's the dog version of the noise method. So when it gets down here, we look through this code. I'm not going to go through all the details, although you can probably figure them out now that you know a little bit about maTe program and coding. You'll see that it's doing some initialization. Here's the in. I was looking for the input. Here's the input where it actually requests the input, does some testing of it with the value 42 and so forth. And there's an if then else that's implemented with the if equal instruction. And you'll see here the code where I create a pig here, and I go to L1, which is down here, or I create a dog here. And the interesting code then is when I come out of the if then else, everybody executes this. And A loads 0, so local slot 0, it contains the reference to either a pig or a dog. And in either case, I invoke the virtual method that's at slot number 3 in the method table. And because the compiler has put the method in the same slot, it doesn't matter whether it's a pig or a dog. It's going to call the correct noise method because it always reaches into slot 3. Just for completeness, remember 1 is the number of parameters being passed to the method. And in this case, there's only 1, which is the this pointer, which was what was loaded from slot 0. Okay, so there you have it. That's the magic of object-oriented programming and virtual method calls. It's done by having runtime type information in the object and then using the method tables to map indices like 3 to a particular method, either the noise method from pig or the noise method from dog. Okay. So that's what's going on here. Let's go back to the layout just real quick to remember what's going on. Again, we're just going to put up the class descriptor, the address of the class descriptor in the first word, and then we'll reserve the second word for native, and if there are fields, they will go after that. Okay, I want to just review that because the next slide talks about garbage collection. If we were going to implement the garbage collector with the VM, we're going to need a few extra bits from the header. Again, this will make more sense when we talk about garbage collection later in the course. But we need at least 2 bits in the header must be reserved to be used by the garbage collector. One is to indicate a block is either free or allocated, because when we go to create an object, we got to go to our heap and look for a block that's available to be used for the new object. And so all the blocks in the heap will be marked as either allocated and use, in other words, or free and ready to be allocated for a new use. Okay, so that's one bit. A bit will just indicate whether a block is in use, allocated, or whether it's free. And we need a second bit that we actually use during garbage collection, during the marking phase of the garbage collector. Again, that will make more sense later, but basically we have to look for garbage. we mark everything that's in use, and when we get done marking, anything that's not marked as garbage can be reclaimed and then marked as free and reused. Okay. Now it turns out that here's one time when having the addresses in maTe be byte offsets rather than word offsets are useful to us, because these two bits then can be plucked out of the bottom two bits of the first word and the object header, because the class descriptor address will be a multiple of 4. It will be pointing to a word. So that means the bottom two bits are available, that we can use them for marking purposes and other garbage collection purposes. Just another note about the garbage collector. The garbage collector needs to know the length of all the blocks. Clearly they're variable length depending on what kind of class and how many fields there are and so forth. So, but in our world here, we can detect that from the class descriptor, right? The class descriptor contains the number of fields. So the length of a particular object is obtained by using the address in the first word and going to the class descriptor, getting the number of fields, adding 2 for the 2 words that are in front in the header, and then if you want the length in bytes, because you're going to call malloc or some other allocator, you would multiply by 4 to get the number of bytes. And if the word was marked as free, then we'd have the length in that first word, or perhaps the length in the second word. We can play games like that. If we don't have a class descriptor that points to the number of fields, then we can just store the length of the block right in the block itself. Okay, just a little side thing that'll make more sense when you think about garbage collection later. Let's look at that second header word, just to make sure everyone understands what it's used for. I pointed at one example. It's going to be used for an integer object. It'll be used for the value. And again, I'm just emphasizing it could be an integer object, or it could be some subclass of integer. Okay, some class that inherited from integer, it's still going to have an integer value in that second word. Second example is string. In this case, now we've got a variable length string that will have to be allocated in a separate block in the heap, and we'll point to that from this second word. I would recommend those strings just be stored the normal C ASCII string way. So it's just a normal char star points to a normal null terminated ASCII string. Table, which we're not going to get into much, is that it's a bigger blob. It's a hash table like thing, and so we have some bigger blob that we allocate to control access and so forth to the table, and we'll point to that blob from here. Now notice that these secondary objects, the table blob or the ASCII string, are allocated separately, and they're going to be in the heap. So they'll need to have a header to support the garbage collector also. If you're implementing a garbage collector. If you're not implementing a garbage collector, then we're just going to probably malloc all of these things, and it won't matter whether these secondary objects have headers on them or not, because we won't have a garbage collector. Okay. All right, let's look at some of the functions in the heap. So there's a function. The most basic one is allocate an object for a given class, right? So what are you going to do when you sit down to write the code? I came up with four things, right? You got to go to the class and get the number of fields. You need to know how big the object is. Okay. Then I go and I allocate a block containing that number of fields plus 2 words. Okay. And if I'm going to write a garbage collector, then I'm going to ask my garbage collector for an object that's that size. If I'm not writing a garbage collector, I'm just going to call malloc to do that. Okay. Once I get that allocated block, I get a pointer to that allocated block, then I can put the class, which is the input parameter, in the first word, and I can return the base address of that block as my reference. So inside of the system, we'll have the base address of the allocated block will be the reference to the object. So again, as I've been saying, these functions are a fairly short amount of code. Let's look at more of them. We also have to be able to have a couple special allocate functions. well, there's a special one for string, I guess. Allocate a string. So it's like allocate object, but now we need to also allocate space for the string. So we set the second word of the object to point to a copy of this initial value. So this initial value, if you look at the details in vm.h, is a char star, and so we're being passed in a pointer to a string, C string. We need to allocate an object for string, then we need to allocate a secondary object for the string value, and then we need to copy the string value into the secondary object and then make the primary object point to the secondary object. Again, not a lot of code there. Okay. Then there's functions that are accessors to these heap objects, like get class given a reference. Remember, the reference is just going to be a pointer to the object, to the base of the object's block. And what do we want to do? If we want to get the class, we just want to return the first word in the block. If we want to get the string value, in other words, a pointer to the string value, then we're just returning the second word. Okay, and similarly, I think that's a duplicate slide. Let's go right on to number 9. Everyone will be baffled what happened to slide 8 when they look at these later. But we have some accessors to get integer value, get an integer, put an integer, again, given a reference to an integer object. And again, you're just reading or writing the second word, right? The integer value is in that second word. You have a reference which points to the base. You just read or write that second word, that's all. Get field is similar, right? We have we're given a reference to the object, and now we're getting a field out of the fields that are stored in the object. In this case, I'm showing a diagram for an object that has n fields. And to get the ith one, I just reach in and get the ith word after you skip over the header. So again, not a lot of code here to write. Okay, and I think that's an exhaustive list, actually, of the heap functions. So again, once you have the big picture in your mind, not too hard to implement it. All right, let's move on then. What else do we have to do? Where's my my big picture? My big picture is this. Again, we've talked about class. We've now talked about heap. Let's move on. The third building block that we need is to implement frames. Again, you should have seen the Java virtual machine lecture. You should have learned a little bit about frames. Let's just review that. You know, inside the virtual machine, there's a stack of frames. And actually, the frame is created for the main block. So initially, when the VM starts up, we create a frame for the main block. And when a method is called, a new frame is created and pushed onto the stack. So there's a frame for every active method, plus an initial frame for the main block. When a method returns, a frame is popped from the stack and deleted. So as we call, we push onto the stack. As we return, we pop off and return to the caller's frame. Okay. Well, what's in a frame? Three things. There's local variables. So every method, when it's running, has potential for having local variables. And those are stored in the frame. Okay, and if it's a recursive method, of course, there's a frame for every active call to the method. So there's copies of the local variables for every active method. Right. Also inside the frame is an operand stack. So while we're executing a method, we may, because it's a stack-based machine, maTe is a stack-based machine just like Java, it's pushing and popping operands on and off the stack, right? When it operates on values, it's always operating on values that are on top of the stack. So addition, the addition method from the integer class, for instance, will pop two values off of the operand stack that's in the top frame, right? It's always operating on the top frame. and then it does the addition of those two values and pushes the results back on. The other thing that's in the frame is the saved PC. So when we created a new frame, it's because there was a method call, and we need to remember in the frame the caller's PC, the program counter for the caller, so that when this method, the new method, returns, we know where to go back and continue execution. Okay. And just a note here that the number of local variables varies, right? It depends on the method. It's a property of the method, and of course there's a field in the method table for each method that describes how many local variables the particular method has. Okay, let's take a quick look at the functions that are available in this frame section. I think it's fairly straightforward, actually. I think so. You'll let me know if you think it's not, and raise questions on Piazza. The first thing, if you look in the vm.h file at the section that describes the support for frames, you'll see that there's one of these void stars. So the frame is going to be a struct. I would think you would want to declare a struct for it because it's got multiple fields you need to represent. And but to the outside world, they don't need to know the details. So we use this void star to the outside world so that nobody gets tempted to go in and touch the inside of the frame without going through one of these functions. Okay, so the view we present to the outside world is that a frame is pointed to by this opaque pointer, this void star. Okay, so what can we do with frames? Well, we can create them. Right, I can create a frame. So if I'm implementing a method call, a method invocation like invoke virtual, I'm going to have to create a frame. I have to know how many locals the method needs, and I have a PC for the caller that I need to save into the frame. So I provide the number of locals for the new frame, the caller's PC, so I can save that in the new frame, and what I get back is a frame, which is a pointer to a frame, actually, we can see internally. When I'm implementing a return instruction, then I'm going to delete the frame. All right, I'm given a frame, I just delete it. So if you have this would be outside of the garbage collector. You'd be using malloc to create the frame. You'd be using free to free the frame. These are not objects, so they're not going to be allocated in the heap. So you'll always be using malloc probably to allocate these things. So you need some kind of implementation, because now inside the frame there's an operand stack. So you need to implement a stack inside the frame. And this is just simply a Boolean that tells you whether that operand stack is empty or not. So given a frame, look at its operand stack and see if it's empty. Again, the details of how you implement that is not important because we're going to access it through these functions. So you can choose how you want to do that yourself. Then we have functions for pushing references onto the frame and for popping a reference off the frame. Again, we only push and pop references because this is a pure object-oriented language. Everything is a reference. So I can push references on the operand stack for a particular frame, and I can pop them off and return them for a particular frame. Okay, and there's occasions when I need to peek into the stack, into the operand stack without popping them. So there's a function to peek operand stack. Again, stack for a particular frame and an index that tells me how deep down into the frame, how deep down into the operand stack I want to look. And again, I return a reference. Given a frame, I might want to check on how long the local slot array is. So I can do that. Again, that was a property of the frame when I created it, right? So inside your frame data structure, you need to remember how many locals there were, as well as representing the individual locals and also. Okay. Then there's functions for getting locals. So if I'm doing an A load instruction, right, I'm going to have to call get locals for the current frame and then which local variable I want to get. And it will give me the reference back that was in that local variable. Or the reverse thing is, given a, I want to do a store. A store would be put a reference into a certain index for the local variables of the certain frame. It's usually you're operating on the current frame, which is going to be the top of the frame stack. I'm going to talk about the frame stack in just a minute. Finally, I have this save PC. I need to get it. I need to put it. Okay, frames are organized in a stack. As I said, every time a method is called, we allocate a frame and push it onto the frame stack. When we implement a return instruction, we pop a frame and free it. So we have a function to test whether the frame stack is empty. This is important so to know when the virtual machine is going to terminate, because we terminate when the main block returns. When the main block returns, the frame stack should be empty. So we're always checking for that case. If the frame stack gets empty, that means the return instruction actually needs to be implemented to terminate the virtual machine, that we're done executing. We're exiting the main block, and so the program is done. Then there's functions for pushing a frame onto the stack and popping a frame off the stack, and also one to retrieve the current frame, which is always the one on top of the stack. So this is a fairly common use. We're just doing operations within the current frame. We need to get that frame from the top of the stack. Okay, so again, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 functions to implement, but they're all going to be typically a few lines of code. You just have to come up with a strategy for implementing the frames. And again, that's up to you. The details of that are not going to be noticeable by another component of the system, so you have freedom there to do that the way you want to do it. All right. Where does that leave us? That leaves us, I believe, with the execute engine as the last component. Again, I'm looking for my master diagram, which of course I've buried in a stack of paper here. Here we go. Right, we've talked about the class, we've talked about the heap, we've talked about the frame. The native code is going to be given to you. We're not going to talk about the garbage collector. So the only thing left is the execute engine itself, which is going to have to know how to actually execute individual instructions. So, like all machines, there's a fetch execute cycle, and you're going to have to implement this. This would be placed into the main function. Remember, so far we've been doing unit testing. We've had main functions just to do unit testing of these components. But at the point we want to actually execute, now the main function is going to be, excuse me, it's going to contain the fetch execute cycle. So here's an outline for how you want to do the fetch execute cycle. Obviously, you're going to initialize the VM. You're already doing that. You're going to then create and push a frame for the main block. Where does execution start? Execution starts at the main block address. So you're going to get the main block address. That's, again, this is a function in the class section. You're going to put that in a variable inside your VM implementation. I would call the program counter. Right? The program counter, like on all machines, is the address of the next instruction. Okay? And the fetch execute cycle is just an infinite loop. It's just an infinite loop, right? This is the thing about computers. They're actually quite dumb. They just spin in this loop forever. What do we do inside the loop? We go to the word pointed to by the PC and we retrieve it. That's going to be the opcode. Okay? We advance the PC to point to the next word in memory. And again, the PC is an address in units of bytes. So I'm adding 4 here to skip to the next word in memory. Then I'm going to call my execute engine, given the opcode and the current advanced, it's the advanced PC, it's had 4 added to it. And that will go out and execute that instruction indicated there. And it may have to fetch additional words from the memory, as we'll see. And it may update the PC, so the return value of execute will be an updated PC potentially. So for instance, a goto instruction or a method call instruction will change the PC as part of the execution. All right, what does execute engine do? Well, it's conceptually anyways, it's a big switch on the opcode, right? You look at the opcode and that tells you what to do. So you switch on the opcode and you implement a particular instruction. As I said a moment ago, you may need to fetch additional words using the program counter because some instructions are multiple words, like a load. The slot number will be in the next word in memory. And as I just said also, you may need to update the PC. So a go-to instruction or an if equal instruction or a method call instruction, they're all going to change the PC, and execute will return as its return value back to the fetch execute cycle the updated PC. So let's look at some example instructions. I'm going to do a simple one, a medium one, and a hard one. And it'll be your job then to extrapolate from those to complete the rest of the instructions that are supported by maTe's virtual machine. So a very simple one is just a const. That's absolutely the wrong header for this slide. I left off something, so let me correct it. It's a const null. Okay. A const null is just push a null reference on top of the stack. And in our world, a null reference would be 0, right? The bits are all 0 in the word. So now you'll see how we used the three components, the frame, the heap, and the class components. Because what I want to do now is I need to get the top frame, and then I just call push operand stack on that frame, pushing a value 0. That's how I would implement a const null. This instruction does not update the program counter, so there's nothing to mess with there. And that's it. So it's a one-liner. To implement a const null is one line using two functions out of our support routines. Okay, I admit that's an easy one, but there's a number of easy ones. Let's look at one that's slightly harder. A load. Okay, a load takes a second word, right? If you look at the description of a load, you'll notice that it wants to know a slot number. So we'll have to deal with that. So first thing is I need to get the frame. So I get the top frame. Then I need to go get the slot number, which will be the next word, and it'll be currently pointed by the PC. Remember, the PC was updated by the fetch execute cycle. The PC was updated, 4 was added to it. So the PC is now pointing to the next word in memory after the opcode. So I can just call get word from code, which again is a support routine, pass the PC, which contains the address. It will give me then the word which will contain the index I want. A load is pulling a local variable out of a local slot and pushing it onto the operand stack, and so that's what we see. We see get locals from the current frame at that index that I just grabbed out of the code stream and push that value onto the operand stack on the current frame. Okay, and then this instruction needs to return an updated PC back to the fetch execute loop. So I need to advance the PC again. Again, it was advanced once to point to the index word, and now I need to advance it again to point to the next instruction in memory. Okay. All right, so this is a medium one. I think this is 4 lines of code. Again, because a lot of the details are handled by these support functions that we've built earlier. We've unit tested them, so we're pretty confident they work. Now it's just write a couple of calls to them in conjunction. We can implement a sort of medium complexity instruction. All right, but there are some tough ones out there, and most of them involve method calls and returns. I'm going to look at a return. By the way, you may be wondering, why is this thing called a load and why is this called a return? A is the Java terminology for a reference. It's the abbreviation for a reference. I don't know why they use A, but these opcode names are just stolen directly from Java. And since everything we have is a reference, we have a load, a store, a return. Again, in Java, because there's primitive types, you'll see things like I load, I store, I return for integer versions of these because Java supports integers as primitives. Here, everything is a reference, so we only have a single flavor of load, store, and return. Okay, well actually we have a second flavor of return because we have a return without the A, which means it's a void function. Nothing is being returned. All right, let's look at a return. Again, you can see it's a little more complicated. What are we going to do? Well, we're returning, so we're going to pop a frame. And then we're going to pop the return value from the operand stack in that frame we just popped. Because the way this machine works is the return value will be on top of the operand stack inside the frame of the method that is returning. We also need to grab the PC from that frame because that's the save, that's the caller's PC. We're going to need to return to that. Okay. And then, as I mentioned a few minutes ago, is that a return from the main block? We have to worry about a special case of shutting the virtual machine down when we return from the main block. And as I mentioned earlier, that's simply, is the frame stack now empty? And we have a function that will tell us that. If so, now we're going to call halt VM, which is this, a second function in vm.c. And what we have to do is we have to halt the VM with a status that's extracted from the integer value that is the return value. So according to maTe's rules, when you're returning from main, you have to be returning an integer object. And what the VM needs to do is take the value from that integer object and pass it to halt VM as the status code for the termination of the virtual machine. Okay. So we have to handle that special case. We're worried about returning from the main block. If it's not the main block that we're returning from, then we push the return value onto the operand stack of the frame that's now on top of the frame stack after we pop the earlier frame. So we just take that return value, we push it onto the operand stack, and now we return PC. And I probably should add here we can free the old frame too. Free the popped frame because we're done with it, and we have a frame function to do that. Okay. So there's a more difficult instruction, and you'll have to ponder a little bit about how to do invoke virtual, invoke special, and so forth. But remember, the maTe documentation, there's a description of what every instruction does. So you want to be looking at that as you write the code. And of course, you want to have vm.h open too, so you can remember what are the support functions I need to have that I can use to solve these problems. Okay. So you put all those pieces together, and it's going to be exciting because you should be able to build the VM and then execute class files. All right, I think I'm going to stop here.